Time on Earth feels steady, but in space, it behaves in ways that sound impossible. According to Einstein's theory of relativity, time doesn't run the same everywhere. The stronger the gravity, the slower time moves. That means near a black hole, seconds can stretch into what feels like years compared to far away in space. Even speed matters. Travel fast enough, and your clock ticks slower than someone standing still. So in a way, there's no single now in the universe. Time is flexible, and space can bend it. Today we will talk about how time works in space. Mind-blowing. So before we start, make sure to hit the like button and subscribe to my channel. 1. Introduction. Why time and space breaks human intuition. Time is one of those things humans assume is universal. On Earth, every clock seems to agree. Seconds tick forward steadily, minutes follow, and days pass in a predictable rhythm. Because of this everyday experience, it feels natural to believe that time is the same everywhere in the universe. But modern physics shows something very different and far more mind-bending. Time is not fixed. It is not absolute. It is flexible, relative, and deeply connected to space itself. In space, time can pass faster or slower depending on conditions. Two people in different parts of the universe can experience completely different amounts of time even if they start at the same moment. One may age normally while the other ages much more slowly. This is not science fiction. It is a real, tested phenomenon predicted by Einstein's theory of relativity. The universe does not have one universal clock. Instead, every object carries its own version of time. 2. Einstein's space-time, the fabric of reality. To understand time and space, we must understand Albert Einstein's revolutionary idea of space-time. Before Einstein, scientists like Isaac Newton believed time was separate from space and flowed equally everywhere. Einstein changed this completely. He proposed that space and time are connected into a single four-dimensional structure called space-time. Imagine space-time as a flexible fabric. When heavy objects, like planets or stars, are placed on it, they bend it. This bending is what we experience as gravity. But the key insight is this: gravity does not only affect space, it also affects time. The more space-time is curved, the more time itself is slowed down. This idea forms the basis of modern astrophysics and explains why time behaves differently across the universe. 3. Special relativity. Time slows down with motion. Einstein's special relativity explains that time is affected by speed. The faster an object moves, the slower time passes for it compared to someone who is not moving. This effect is called time dilation due to velocity. For example, imagine a spacecraft traveling close to the speed of light. Inside the spacecraft, everything feels normal. The astronauts talk, eat, sleep, and work as usual. But from the perspective of someone on Earth, time inside the spacecraft is moving much slower. If the spacecraft travels for 5 years, ship time, decades might pass. On Earth, this has been confirmed through experiments using extremely precise atomic clocks placed on fast-moving jets and satellites. Even though the differences are tiny at low speeds, they prove that time is not absolute. It depends on motion. 4. General relativity. Gravity changes time. While speed affects time, gravity also plays a major role. According to general relativity, gravity is the curvature of space-time caused by mass. The stronger the gravity, the more space-time bends and the slower time moves. This means that time runs slightly slower on Earth's surface compared to higher altitudes like mountains. The difference is extremely small, but it is measurable with precise instruments. The closer you are to a massive object, the slower time becomes. For instance, near a neutron star, a collapsed core of a massive star, gravity is so intense that time slows dramatically. A few hours near such an object could equal many years far away in space. This shows that gravity is not just a force pulling things together. It directly controls the flow of time itself. 5. Black holes, the ultimate time dilation machines. Black holes represent the most extreme environment for time distortion. They are created when massive stars collapse into a single point of infinite density, creating gravity so strong that nothing, not even light, can escape. Near the edge of a black hole, called the event horizon, time behaves in a bizarre way. To an outside observer, an object falling into a black hole appears to slow down more and more. It seems to freeze at the edge and never fully cross it. The light from the object becomes redder and weaker due to extreme gravitational effects. However, from the perspective of the falling object, time feels completely normal. The object crosses the event horizon without noticing anything special. At that exact moment, this creates one of the biggest mysteries in physics. Two observers experience the same event in completely different ways. 6. GPS and real-life proof of time dilation. Time dilation is not just theoretical. It is used every day in modern technology. GPS satellites orbit Earth at high speeds and are also far from Earth's strong gravitational field. These two effects influence time in opposite ways. Because satellites move fast, their clocks run slightly slower. Because they are farther from Earth's gravity, their clocks run slightly faster. Engineers must constantly correct these tiny differences. Without these corrections, GPS systems would become inaccurate by several kilometers every day. This proves that relativity is not just a theory, it is essential for modern life, navigation, and communication systems. 7. The twin paradox. Aging differences in space travel. One of the most famous examples of time dilation is the twin paradox. Imagine two twins. One stays on Earth, while the other travels in a spacecraft at near light speed. When the traveling twin returns, they are younger than the Earthbound twin. This happens because time passed more slowly for the traveling twin due to high speed. Even though both experience time normally in their own reference frames, their aging differs when they reunite. This is not a contradiction. It is a direct consequence of relativity. If humans ever achieve high-speed space travel, this effect could become very important for interstellar missions. 8. The universe has no single now. The most shocking conclusion from all of this is that there is no universal present moment in the universe. What is now for one observer may be in the past or future for another. This means that simultaneity is relative. Two events that happen at the same time for one observer may occur at different times for someone moving or located in a different gravitational field. Some physicists suggest the block universe idea, where past, present, and future all exist together in a four-dimensional structure. In this view, time does not flow, it is more like a landscape we move through. Although this idea is still debated, it highlights how strange time truly is at a fundamental level. 9. Time is part of the universe, not outside it. Time and space shows us a deep truth. Time is not separate from the universe. It is part of it. It is shaped by motion, gravity, and the structure of space-time itself. It can slow down, stretch, and differ depending on where you are and how you move. What we experience as a steady flow of time is only a local effect of Earth's conditions. In reality, the universe is filled with countless different timelines happening simultaneously. Near black holes, in fast-moving spacecraft, and in deep space, time behaves in ways that challenge human imagination. The more we study the universe, the clearer it becomes. Time is not simple. It is one of the most mysterious and flexible properties of reality itself. Now, if you like this video and would like to see more like it, please give it the thumbs up, leave a comment, and click the button to subscribe.